Guys, in the last lecture we understood how to calculate the voltage gain for the given circuit. Okay, so in the same way one more question is given. This is the given circuit. If you observe in this circuit, simply we are requested to calculate the value of voltage gain input between output, and whereas they have given one more clue that the value of beta is very large. That is the only thing that is given in the question. Sometimes you have to understand what they will be doing is either they will tell that the value of beta is very large, or they will directly give the value of beta but it is in very larger value, like it is in 700 or 800, 1000. So in that case also, directly by observing the value itself we can understood that yes, the value of beta is very large. So approximately we can assume the value of I base DC current is equal to 0 ampere. Base current equal to 0 ampere. Okay sir. So when the value of base current will become 0, we can say the value of collector current will be approximately equal to the value of emitter current. You can apply the same for AC, right? When we are drawing the equivalent circuit, beta is very large, so the value of base current is automatically going to be 0, and the value of collector current and emitter current will become approximately equal. Okay sir. So let us start analyzing this circuit. How will you draw the AC analysis? While doing the AC analysis, it is very important. See, you no need to check whether it is where ground is there, where supply is there, right? What type, what is the name for this circuit? Nothing is required. We know collector is connected with the ground, so it is called common collector configuration. If emitter is connected with the ground, then that is called common emitter configuration. If base is connected with the ground, then that is called common base configuration. If you observe the question carefully, given it is NPN transistor, by observing the direction of the current we can guess. And the supply voltage is given, voltage given across the emitter terminal, whereas collector is connected with the ground. It means that is called a common collector configuration. First, try to understand how to derive whatever the procedure that I told you, just to follow it. Now you should think, sir, whether the value of RE is required or not. For that, what I am suggesting you is first to do AC analysis. At the last point, when you are trying to get the answer, suppose without knowing the value of RE, if you are unable to get the answer, then do DC analysis, calculate the value of RE. That is best way, okay, because sometimes without knowing the value of RE also we can bring the answer. Let us see how will you draw the AC equivalent circuit. The procedure is we have to deactivate all DC sources, right, and then we can draw the circuit. If capacitor is there, then capacitor will be short circuited. Anyway, capacitor is not there in this question also. There is only one DC voltage source. I have to deactivate it by connecting it with the ground. Then if I will draw the equivalent circuit, see there, sir, here also we are having ground. It means this 100 kilo ohm resistor is connected with the ground. See there, it is connected with the ground, and this 200 kilo ohm resistor also connected with the ground. While applying DC, this is also going to be connected with the ground. Now from this point, if I am observing, suppose if I am calling it as A, between A and ground we are having 100 kilo ohm. Between same A and ground we are having 200 kilo ohm. It means these both are connected in parallel. Can I draw like this? See there. How I am drawing is, I am taking AC supply here, yes, and from here I am going to just connect them with the ground. That 200 kilo ohm resistor and then that 100 kilo ohm resistor, both are, can we draw like that? Of course they are connected in parallel now. From this we can easily observe that, sir, this bit, both will become parallel. After that we are reaching the transistor. Now how will you replace the transistor? Anyway, we are in base terminal. From base terminal, now you can draw the equivalent circuit of the transistor. Again I am taking RE model. RE model means beta times of RE. Then here we have to connect one current source. That value is beta times of IB. Of course that is equal to collector current IC. And then we know collector terminal is already connected with the ground. Yes or no? See there, collector terminal is already connected with the ground. Now if you observe the emitter terminal is connected with this. Now this is the emitter terminal. Emitter is connected with the 470 ohm resistor. Anyway, after that what I have to do? I have to deactivate that 15 voltage source. Now where we are going to measure the output voltage? Observe. See the output voltage we are measuring across the emitter port, because this is common collector configuration. So from here only we are going to measure the output voltage. Okay sir. Now tell me what is the direction. So this is the base current. Yes. And here we are observing the collector current. So this one is going to be your emitter current IE. Since the value of beta is very large, whenever the value of beta is very large, directly I can say the value of base current is approximately equal to 0 ampere. One thing you all have to notice here, I am telling that the value of base current is approximately equal to 0. But some of you are confusing that, sir, so then what I can do is IC equal to beta times of IB, sir. When the value of IB equal to 0, collector current also will become 0, sir. No, I said base current is approximately equal to 0. It means it is in microampere or it is in nanoampere. But the problem is when the current is very less, but the value of beta is very, very large, while multiplying a large factor with a low value, automatically you will get some reasonable value. It means collector current will not be equal to 0. Only base current alone will become 0. So in that case, see there, if you observe from the input side, you can make this value of base current is approximately equal to 0. It means, what is the voltage drop across the resistor? Voltage drop across the resistor will become 0 voltage. Why, sir? Since we are approximately equating the value of current equal to 0, no? So 0 into beta times of RE also will become 0. Yes, sir. Anyway, let us compress the circuit further and then we will bring the relation between input voltage and output voltage. First, let us see. From this, I can write the output expression directly. Output voltage V0 equal to, since we are measuring the voltage across the 470 ohm resistor only. See there, where is our output port? This is the output port. It means this is plus, opposite will be grounded, minus. So that is nothing but across the 470 ohm resistor, whatever the voltage that will be dropped, that is your output voltage. That can be written as, since the current entering across the 470 ohm resistor is IE. So voltage drop can be written as emitter current IE into resistor value 470 according to Ohm's law. Treat this one as your equation number 1. Next, see there, this 100 kilo ohm and 200 kilo ohm both are in parallel. Yes, sir. So if I will reduce them, we can compress like this. Just observe, almost all the circuits will be same. You can easily solve the questions. I am just compressing it. And I am directly writing that 100k is parallel with the 200k. That is the representation of parallel resistor. Okay, sir. Since the value of current will be 0, now see there. Now this is going to be your input voltage. Since this input voltage and 100 kilo ohm resistor, this resultant value resistor, both are in parallel. So same input voltage will be appearing here also. Yes, sir. Then here we are having our beta times of RE, but there we are not going to observe any voltage. Since the current flow through the circuit is 0, so the voltage drop is going to be 0 voltage. Beta times of RE into 0 will become 0. After that, here we are having RE. So the emitter current IE is entering here. The value of RE is given as 470, current entering point plus leaving point is minus. Now it's time to apply KVL for this loop in order to solve this equation. Just KVL. Always we have to apply KVL only in order to bring the answer for any question. So let us apply KVL. Minus input voltage plus, I am not considering beta times of RE here because that value is 0 already, plus here we can consider 470 into emitter current IE equal to 0. Yes, sir. From this, what is the value of input voltage? Input voltage equal to 470 into emitter current IE. You can treat this one is your equation number 2. That's all. What is the question? The question is voltage gain is what? Yes, we brought the relation between input and output. See there, input voltage is available here now. Yes, sir. Output voltage is available here now. Both are in emitter current only. So now if I will take the ratio between output voltage and input voltage, what you will be getting? Sir, output voltage is 470 into emitter current IA. Okay, sir. Input voltage also same 470 into emitter current IE only, sir. What is the conclusion? It will get cancelled out. Resultant, wow, we are getting 1. So it's a beautiful conclusion. So the conclusion is voltage gain of the given circuit is equal to 1. Do remember this relation. Now tell me, I named this circuit is what? Common collector configuration. Yes or no? They only told, actually I did not told. In the question what happened is, according to the given data, I understood that collector terminal is connected with the ground. So this is called common collector configuration. For the common collector configuration, what we observed is the value of voltage gain AV equal to 1. That is one of your examination question only, not 1 volt. See there, for the gain there is no unit, that is 1. So always it is fixed. Hereafter, remember one thing, whenever you are observing common collector configuration in your examination, it doesn't matter how big your circuit is, how big data they have given. Whenever you are observing common collector, always the value of voltage gain is fixed, that is 1 only. Just to keep a note, this is very important, because directly you can keep, you don't need to derive these many things. I have derived these things in order to let you all to understand how to calculate the voltage gain. And do you remember one more thing? The surprised thing is, in this question I have not estimated the value of Re, whereas in the last question it was required to calculate the value of Re. Without knowing the value of Re, I was unable to calculate the voltage gain. That's why I have derived the circuit in DC analysis, and then we were derived the circuit in AC also. But here I was directly driving the circuit in AC, and I also understood that Re is not required to calculate the value of voltage gain. So hereafter, what is the conclusion? Whenever you are doing AC analysis, first do the AC analysis, go to the last point, then check whether Re calculation is required or not. That is, whether the DC analysis is required or not. That conclusion you can get it at the last point of AC analysis. After that, if it is required, then you can do. If it is not required, then you can skip. So this is all for this lecture. Remaining things we will see in the next class. Thank you all.